Okay, welcome to the third week of software security class. So now we only have 44 people, 20 people dropped, which is good. I hope the rest of you who stay here, you like this course. Okay, that's what usually happens before. A lot of people will drop at the beginning, but the people usually who stays will enjoy this class very much. Okay, so I'm a little bit sick today, so it's not COVID, but just a little bit allergy. So first, in the homework, there is a crack me 32-bit. I want to talk about this one a little bit. So how do you approach this one? So for most of you who haven't done any reverse engineering, so when you first time look at a program like this, crack me 1, you probably have no idea where to start, right? That's what you feel. So usually something like this, what you should do is you just try to get as much information as possible first, kind of like a reconnaissance. Consider yourself as an attacker. You're trying to attack this software. The first step you are doing is a recon stage, right? Try to get as much information as possible. You can use all the tools we have learned so far. You can do a file on this one. Do a file on this one. Then you learn this is a 32-bit L file. Then this is all static analysis when you do this. When you do this, you're not running the program. And to understand more about it, obviously you have to run it, okay? But this program is when you run it, it doesn't show anything. But when you run it, you can also give it some arguments, right? Or even more, let's try. Or you can even feed it with some other input. So for this particular one, what you also need to do is you need to try to, because the goal of this challenge is teach you how to do reverse engineering. So you will try to understand what this program does. So to do that, you can download this program. Where's here? You can download this program using the search button here, download challenge. After you download that, you can throw this into like a Battery Ninja. I recommend you just to use the free version of Battery Ninja. You can also use the object dump, but Battery Ninja is easier for you to use. You can use the free version, core version, for example here. I already loaded this upload here, so I just click this one. So from Battery Ninja, you can say this program has this many functions. And usually you look for the main function. That's where the program starts, right? So you can go to the main function, it shows the disassembly. And Battery Ninja has a very good feature, which is a decompiler. And it's a free decompiler. A lot of tools, for example, IDA Pro, the decompiler is not free. So here you can click the high level IL. IL means intermediate language. If you click high level IL, it's very close to C, but it's not C yet. So if you click this, you can get a feeling. So this is kind of like a C program. And you can get a feeling what this program is doing. So this is the main function. You can use the space bar to have two different views. One is this control flow view, or this kind of like a flat view like this. Using space bar, you can get a flat view. So maybe for someone, this is more easy to understand. So look at this. This is the main function. And this is the function prototype you are familiar with. The main function takes up to 3 arguments. The first one is argument count, means how many arguments are there. The second one is the array of the argument pointers. The third one is the environment variables. A lot of programs will just set this one as 0. The second one sometimes is also 0. Then let's see what this program is doing with this. So here we can say there is comparing using the argc. It tries to check if argc is 2. okay? And compares argv1. Argv1 is the command line argument it gives to the program. The first, so argv0 is the name of the program. Argv1 is the command line argument you give to the program. So it's doing a stringness of whatever you type there with a predefined string p here. So if you click here, you can say what p is. Okay, p is this string. So this is where you start try to understand this program. From there, so which means if you do not give it two arguments, you do not provide a command line arguments, it will strictly go out. Okay, only if you give an argument and the argument length is the same as that, it will keep going and trying to do some comparison. Try to figure out, yeah. No, this one will return. Let's shoot. It's here, right? I'm going to run this. No segment photo. Segment photo, you're talking about another one. You're talking about the overflow local 2. Yeah, that one because I was my program was checking the second argument. However, I was not checking if there is a second argument. I was directly accessing. So if you do not give that, it will be segment fault. So this one will not have that. Okay. So your job is to try to understand this piece of code. Okay. Try to understand this piece of code and somehow make this piece of code to trigger a print flag. That's your goal. Okay. Any questions? Okay, good. Yeah. Okay. So if by Wednesday you still do not know how to do this one, I have an office hour right before the class. So you can go to the office hour, you can discuss more details, but I still want to give you guys 2 more days to figure it out by yourself. Okay, so last class, we started talking about stack-based buffer overflow. We saw 2 examples to overflow local variables. Today, we are doing something even more interesting. We are not overflowing the local variables. We are going to overflow the return address on the stack. So this is your first control flow hijacking attack. So I already said that the default C function convention, calling convention is called the C declare, CDEL. So we have saying 2 carefully designed examples, vulnerabilities. They are far away from real world examples, real world programs. In real world, it is actually more useful to overflow either the return address on the stack or the frame pointer on the stack. So previously we were only overflowing the local variables. So in this calling convention, most C functions are using this calling convention. In this calling convention, the return address is saved onto the stack. So we have different names for that return address. It could be saved EIP, saved RIP. And since that is the address of a code, so itself is a pointer. From C programming language point of view, everything points to another address that's a pointer. And if we're pointing to a code, that's a code pointer. So return address is actually a code pointer. Then besides that, we also save the previous function's frame pointer onto the stack. So that one is actually we solve the code assembly code. we save the EBP or RBP. So that is a save the EBP or RBP. So that one not directly point to any code. It's pointed to some other functions function frame. So that is a data pointer. So if we look at the second overflow local example again, this is what we saw last week. So what we did there is we gave, so this program basically asked us to input something from the argument, command line argument, right? So there is a buffer, 6 bytes. We overflowed this 6 bytes. We put 6 bytes of garbage there. Then we put something more, and that will overflow the local variable j, right? So we did this. If we, let's do this again. Go to overflow local 2. I'm a little bit slow today. So, week 2. Python 2. Print. We want 6 bytes of garbage. So I will just use A as garbage. Then we plus 1, 2, 3, 4, 5, 6, 7, 8. So when we do this, we will overflow that local variable j and overflow it with that exact value we wanted. So that's why the program will go to this path and print out the fact box. However, if we keep flowing this, let's say instead of just put 1 of those 4 bytes there, we put 5 of those 4 bytes there, right? We put a multiple 1, 2, 3, 4, 5. So what will happen? What? Yes, we will overwrite more things on the stack. But what will happen if we overwrite more things on the stack? But why do we get the segmentation fault? What? There is no what? Okay, but why does the program has to go back to the corner? The program doesn't really have to go back to the corner, right? The program can, well, let's say, maybe program is not the right word here. The PC or the EIP has to point to some valid code address. Doesn't have to be the original, but we override the original, right? So when we do this, what will happen is eventually we will get a segment fault. But the reason we get a segment fault is some of those values will be popped into EIP. But when we pop that into EIP, then that value will be treated as an address for code. But this value may not be a valid address for code. So when the PC, when the EIP start execute, the processor start executing instruction from there, that may not even be a mapped memory address, may not exist. So it will trigger in the operating system, it triggers a general fault. It's trying to access a memory location that doesn't have the code, should not be executable. That's why eventually it generates this segment fault. Okay, so next, what I'm going to do is we're going to debug this piece of code to say how exactly that happens. And the reason I want to show you how to debug this is because you need to get familiar with GDB in this case. So we're going to debug this program like this. But just using the server, we are using a simple GDB here. we do a GDB, we do this, then we want to, first we set a breakpoint at the main function. Do we have a valve? Yeah, let's just set a breakpoint at valve as well. So B is how you set a breakpoint in GDB. So we said now we have two breakpoints, one in the main function at the beginning of main function, another one at the beginning of valve. So next we want to do is we want to run the program. Okay. So when we run this program, we still want to give it that command line argument. This is how we do the same thing. Can I just copy that? Let's copy this. Okay, so I'm going to copy it here. So now we are going to run this program, and we know this is going to crash the program. We just want to figure out how exactly it crashes the program. Okay. Now we are in the main function. We want to keep running until it hits the valve. So now I use the same means continue. Now we are at the beginning of valve, which is here. Okay. So let's say what we want to do. We want to do a. We want to say the binary code of this. We can do a disassemble command. Then it shows us we are in the valve. We are right now actually at here. The next instruction to be executed is this one. And what we want is we want to keep running until the string copy, because the string copy is a vulnerable one, right? So let's keep running, and let's do n to 239. 239 is a string copy. So we do n here. Oops. So we do n here. Did I accidentally quit? Where are we? Oh, yeah. I accidentally quit, but you can see that value was popped into EIP. That's why it's not working. Let's do it again. We are in valve, so we keep running. Why? Oh, I have to use S here. Sorry. Say here, then here I'm using S. S means step by step. So where are we? Looks like I have to use SI instead of S. Well, because the GDB is a little bit different here. Say, okay, so I'm using SI. SI means step instruction. Okay, so we want to get to the instruction 293. So we're doing SI until 293. Okay. So right now we are at here. We're about to execute string copy. So let's evaluate right now. So right now we haven't overwrite anything, right? Let's evaluate what is on the stack. To do that, we use the exam command. We can exam maybe 10 keyword hex. Then we can exam at where EBP points to. So remember, the EBP should point to the saved EBP, right? So that's why the EBP points to the saved EBP. This is a saved EBP. The EBP plus 4, what is this? Anyone remember what is the EBP plus 4? What? No, EBP plus 4 is the saved return address. So this one is actually the saved return address. Look at this, 5655. This start with 56. This is somewhere in the code section, right? So if we do a disassemble the main function, then you can say this 2E8, okay? That's the return address. Let's find the return address somewhere here. 2E8, see? It's here. That's a return address because here we call the val-foo, right? We call the val-foo. So when we call val-foo, the return address should be the instruction after we call val-foo. So this is a return line. So that's why this address is pushed onto the stack. So right now, before we do the string copy, what we have is this is what the stack look like. This is the main functions stack frame address. This is the return address for the val-foo, which is an address in the main function. Then let's just do a memory copy, a string copy, using let's do a next instruction. Okay, now we are in 298. I believe we finished the 298. Okay, see now we're here, which means we just finished executing the string copy. Then let's say if we overwrite everything on the stack, we use the same exam. We want to examine 10 items. Each item is 4 bytes in hex. That's why I use hex. Then where is the address we want to examine? We want to examine where EBP points to. So now you can see EBP is overwritten. The stack is overwritten. We gave it 5 there, right? It happens to overwrite the pointed return frame, the previous function's frame pointer, and also the return address. Okay. So right now, our PC is here. So we just keep executing this using, let's say we set a breakpoint out here. That will be easier. We set another breakpoint here. So if you want to set a breakpoint at some address, you need to use a star and that address. Now we have the start breakpoint. Now we keep running. Okay. So you see also another thing I want to show you is when we debug this, it shows it cannot open the flag file. That's because when you debug, the program cannot do it's not a setUID program anymore. That's a kind of like a security feature. You cannot debug setUID program when it and also make it run on the root. Okay, but you run it, it actually is a setUID program. Okay, so now let's say where we are at. We are at here. So which means we are going to execute the return instruction. Remember what the return instruction does? The return instruction only does one thing. It will pop whatever ESP points to the EIP register. Okay, so again, do a print EIP. This is the current value of EIP. Then we can do a print ESP, and you can see this is where ESP points to, which should be if we examine that address, we examine one. So the EIP points to that value 1, 2, 3, 4, 5, 6. So what will happen next? We do a SI. It will pop that value into EIP. Okay. So now EIP already has this value, but we haven't executed any instruction at this address yet. Not yet. So right now there's no segment fault. You see that? There's no segment fault. So let's see what we have at that address. We may not have anything there. Let's try. So you can say, well, try to access that address at GDB says cannot access memory at that location. That memory is not even mapped. So next, the CPU is going to fetch an instruction from a memory location that doesn't exist. That is when the segment fault happens. That's why the program crashed. Okay, so that is how exactly everything happened there. So using that example, we change this example a little bit. Then we can go to buffer overflow where we want to overflow the return address. Let's see. Okay, so this is the overflow return example. What? This is a similar program like before. We have a main function. The main function will print out the address of the print secret function. There is a function called print secret. This function doesn't really do much. It print out flag, then exit. Okay. So the main function will first print out the address of that. This is not really necessary, but I just want to make it easier for you guys. Now after that, it calls the val foo. Val foo has a buffer which is 6 bytes in C code. Remember, 6 bytes in C code doesn't mean the binary code. The address between buffer to the saved EBP is 6 bytes. It only means it's more than 6 bytes. The compiler may generate more bytes there to reserve more bytes there to make things faster for better alignment, those reasons. Then it will cause the val foo will call the get function. So the get function will take input from stdin, standard input, not command line. So the problem of get function is same as string copy. You can put a lot of data there. So what will happen is you can overflow the buffer, you can overflow everything higher than the buffer. Okay, then it returns. So if nothing bad happens, this function will successfully return. Then the main function will print out IPT the full. All right, so that is what should happen if you do not try to be an attacker. So we have the here overflow return 1. So if we run this program, so we do not need to give command line arguments, like I said, because you use guess. It will print out the print secret. Then we just put some random data there. It will print out IPT the full. Okay. Even if you give it more than 6 bytes, it will still. Let's try 6. We need to do some disassembly to see how many bytes we can overwrite. Even 7 bytes, still PD the full. I think 8 should 1, 2, 3, 4. 8 is still PD the full. Okay. So if we want to, so the goal of this one is we want to overwrite the return address on val foo for val foo, and we are going to overwrite it with the address of print secret, so we can print out the secret. That's our goal. Is that goal clear to everyone? Make sense? Okay, so let's say how we can do that. So left hand side, the disassembly of val foo. Right hand side, I'm drawing the stack. So try to make yourself like a Turing machine, so we can do it step by step, understand what's going on here. At the beginning of the val foo, the ESP will point to the return address. The return address is part of the main function. It's pushed there by the core val foo function instruction, which is in the main function. Then the first thing in val foo is we push EBP. So because this is a push, so ESP will move down and the ESP will point to the old EBP. Then we have a move ESP to EBP. So now EBP, ESP, both of them point to the saved EBP. Then we have a subtract ESP to of 18 in hex. That's 24 bytes. Okay. So now ESP points to some place lower, and that lower place is 22 bytes away from the saved EBP address. So this part is 24 bytes or 18 in hex. Then there's another subtract. If you ask me why the compiler is generating code like this, I don't know. Okay, this is bad optimization. The compiler can generate a better code, but the code I'm looking at is like this. So EBP moved another 12 bytes down. Then we note effective address EBP minus E to EAX. So EAX points to somewhere, which is EBP minus E. Then we'll do another push EAX. So the EAX is pushed here. Then we call gets. So why we are doing this push is because we are setting arguments for the function gets. Right? The function gets takes one argument, which is an address where you want to write the data to. It doesn't care where the data is taken from, because the data is always input from the std in, standard input, right? But where you write to is here. That's why when you see the gets, you look for its argument. The argument is on stack, and you can say there is a push. But the push, you can say the address is in EAX, then you keep going back. So this is kind of like a backward slicing in programming. In program analysis language, this is called a backward slicing. You're trying to figure out the instructions that are related to these gets. Then you say, then you can figure out the destination for your input is at EBP minus E. Okay, so EBP minus E obviously is higher than EBP minus 18 in hex here. Then after the gets function itself will also use a stack, right? It will generate a lot of temporary local variable here. It may even call other functions. So the stack will keep going down, but we don't really care about that. Okay, we only care that after the gets, the stack should be balanced. Before we call the gets, and after we call the gets, the ESP should point to the same place. In the between, a lot of things could happen, but we don't need to worry about that. So after that, we are going to end this up and eventually return. Okay, so let's compute here. How many bytes exactly we need to override here? The address of the buffer. Yes, here. The load effective address instruction. Load the EBP minus into EAX. So that means the destination is at EBP minus E. It is the only variable. Yeah, so this one is not the string copy. String copy has two, destination and source. Gets only has one, okay? That's where you can use man to do a gets. You see, gets only take one argument. That is the destination. There is no source. Source is the std, it's whatever you type it. Yeah. So let's try to, so now we know that let's call this variable buffer. We know that the buffer is at address EBP minus E, right? So if we want to overwrite return, how many bytes do we need? First, we need E bytes to overwrite the buffer. Then we need another 4 bytes to overwrite the saved EBP, which we do not really need to override it, but this is a sequential override anyway, so there's no way we avoid overwriting this. Then we need 4 bytes of the real return address, right? So that's how many bytes? E, what is E? C is A is 10, B is 11, 3 is 12. Like I said, I'm only just slow today. E is what, 13? 14? Okay, E is 14. So then we have another 4 bytes, so we need 18 bytes. Okay, we need 18 bytes. Then we need the return address. Basically, we need 18 bytes here. Oh, no, this is wrong. Should be some 18 bytes. Yeah, this is correct. 18 bytes, then the address. So after that, we can put any 4 bytes here. So we can one program can jump to any address we want, and our goal is to make it jump to 2 possible addresses. The first one is, let's jump to the function print secret. So you can print us the secret. So let's say if we can do that. So this one takes input from std in. So we have to do a Python 2. In our system, we also have Python 3. So if you are more familiar with Python 3, you can use Python 3. We do print. We need we do 18 bytes of garbage. We don't care about that 18 bytes. Then we put the address of the print secret function, which I printed out conveniently for you here. So that's why the address should be 28, 63, 5556. Okay, I missed something here. Should be this. Then when we do this, Python will print out that value for us. And we want to pipe this value into the program because the program takes data from std in. So we pipe it out to it. Okay, so far it makes sense to everyone. When we run this, it will give us a flag because we call into the print, because we call into this print secret function. Okay, what is the other way we can also get the flag without calling to the print secret function? Yes, we directly print out a flag function, right? So how do we get the address of the print flag function? Yes, we disassemble, but you will find out, let's say if we do an OBJ, another easy way is just use another tool called nm. So nm, then we do, so nm will give us the address of all those symbols. You can say, let's try to find print flag. You can say print flag, this address doesn't look like a runtime address, right? That's because this is offset. At runtime, there is first a base plus this offset, you get the real runtime address. But if you look at the main function address, they're close, okay? So the beginning of those should be the same. Or let's say, oh, this is print secret. Print secret is 1328. Print flag is 1280, okay? So which means we can change this address a little bit. Here is 13, which means here is 12, which means this one we should minus 1. So this one we get 62. This one is not 28 anymore. This one is 8D, right? So now we're not, so by changing this, we're not return into the print secret function. Instead, we directly return into the print flag function, which will also give us a flag. So if we do this, we get the same thing, flag, right? Okay, how did I get the address? Okay. So first, when you do a nm or you do the object dump, what you get the address is like the offset address for a special let's say a section or segment, right? But at runtime, that segment can be loaded at some base address, and that base address could be dynamically generated, not necessarily always the same. So on the server we're using right now, it is always the same because we disabled the security protection for the ASLR there. So previously already know the print secret is at this address 556556328, right? And if you look at the static address of this, you can say this one is 6328. This one is 1328. Okay, which means the offset is something like this: 56556 like 5, right? So they should have the same offset. That's why when I calculate the address for print flag, I would just minus 1 here and change the last byte to 8D. Does that make sense? Of course, another way to do this is we just use GDB. We debug this. We debug this. We debug this program. We set a breakpoint at a val2. We run this program. Now we just print out. We use P to print out the address of the function. The first one is what? Print secret. I don't remember if there's a. Oh yeah, print secret. Okay, so you can get the address. You can also do a print flag. Now you can get the address. Okay, so this is how you get the address. So if we quit, if we get off here, so those two ways, either way we successfully get the flag. However, there is a minor difference. Let me see. How do I compare this to you guys? Let's say this one is, okay, let's do it again. Another address. Okay. Either approach, we get the flag. However, there is a minor difference. Can you identify what is different here? Yes, one of them has a segment fault. So this one we directly call into print flag. So the one we call into print flag eventually triggers segment fault. However, the one we call into return to print secret, there is no segment fault. So let's look at the code to figure out why. The reason is here. When you call this print secret function, before the function returns, it calls exit. Exit means the whole process will exit. So this print secret function never returns. Okay. However, you do the print flag directly, the print function eventually it will return. And the return relies on what? Relies on the data on the stack. Returns relies on that saved EBP. Okay, so when we do that overflow there, we did overflow the saved EBP address, this address. We did overflow this, which is supposed to be the points to the main function's stack frame, but now it points to somewhere else. So eventually, when the program leaves that address, it will trigger a segment fault. But that print secret function doesn't give it. Print secret function doesn't give it a chance to return. That's because of exit. Okay. So the exit means it will not return. The process will be killed. Okay. This is the first overflow example. Any questions here? Good. Let's see. The 64-bit version is actually the same as 32-bit version. The only difference is the address would be 8 bytes. So let's take a look at the next one. Okay. So this is a 64-bit version. We do a file on this one. You can say this is 64-bit. We do a object dump on this one. We look for the Overflow function. This is the Overflow function. Can someone try to tell me where the buffer is? This is 64-bit, yeah. Where? Well, this one? Okay, why is that? Yeah. Yeah, seems like, yeah. But you can see this one, there is no push, right? Why there is no push? The 62-bit version, we say push EAX, but here we do not say push. It's because we discussed last week. For 64-bit version, we do not use a stack to pass the arguments. We use registers. Right. Here, only one register is used. That should be EAX. No, should be EDI, I guess. Let me check last week's slide. I think the first one should be 64-bit version. Sorry about that. Where is it? The previous class. Where is it? Last class? It's yeah, it's here. Should be. Oh, should be here. This one. Okay. So for 64-bit version, the first argument goes to the register RDI. The second argument goes to RSI. The third one goes to RDX. Okay, that's the order. So we do not use a stack. So 32-bit version, we use stack. That's why you see a lot of pushes. But 64-bit version, you say move to those registers. So remember, the first one is RDI. So now go back here. Is so this is a function called gets. So we know when this instruction execute, whatever RDI has is our buffer. So we go look for where is the RDI. Then we say here we move RAX to RDI. Then we know RAX is what we have. Then we move up here. We can say RBP -6 is RAX. So it means RDI is also RBP -6. So in this case, our buffer is at RBP -6. Yeah, I have a question here. So insert. So this is called convention. So all people who design compilers, they should follow those rules. I think those rules are defined by Intel. Intel say when you design compiler, you should follow this convention. you should put the first argument in RBI. If it's a 64-bit program, you should put the first argument in EBI, second argument in whatever. If this is a 32-bit program, then you should push them the argument onto the stack from the right to the left. Yes, 64-bit version, yes. 32-bit, everything is pushed on the stack. No. First of all, 32-bit, there is no RDI. Right? No, it's not. It's only, well, like I said, I mean, if you want to push something on the stack, first, probably you have to put it in a register, right? It doesn't really matter what that register is. What matters is it pushed onto the stack. Okay, so you can see here, you can see this is the same source code, 32-bit and 64-bit, but the address of the buffer is actually different. So the 32, we saw that in this slide, the 32-bit version, the buffer's address is EBP minus 18, right? However, in the 64-bit, the buffer's address is RBP minus 6. It's more faithful to your C code actually, because in C code you only ask for 6 bytes of buffer. Remember, in your C code you only ask for 6 bytes of buffer. But 32-bit version after compare, what you get is you actually have 18 bytes there. But the 64-bit, you can say you really only get you really only get 6 bytes here. Okay. So after that 6 bytes, then what do we have? We have the saved RBP, which is this is RBP is 8 bytes. Then we have I don't have a figure for that. Then we have 8 bytes of return address, right? So let's try to overflow this one. First, let's try to get the address of, I think my program will print that out. Okay, so the program will print out, this is the address. This is a much longer address. We want to exploit this one. We do a Python 2. This time we only need 6 bytes of garbage. Then we plus, we need another 8 bytes of garbage for the saved RBP. So here we need 14 bytes, right? Then we have the return address, which should be 8 bytes. So we have, let's start with the lowest one. 95, 52. Ooh, I'm not sure how many 5 are there. 1, 2, 3, 4, 5, 6, 7, 8, 9. Should be 9 5s, including this one. 1. Okay, so 9. So those 2 should be zeros. Okay, let's see if it works. We pipe this into web 2. Okay, this is how we get. This is how we call print secret. We can do the same thing for the print flag. See, the print flag is 1209. Print secret is 1295. So we only need to change the last byte. This 95 changed to 09. Okay, we get the same thing, but segment fault. So in this case, I didn't use GDB. You can use GDB to do that. Yeah. So in this case, actually my program print out, because this is the very first one. My program print out the address for you. But you need to pay attention here is, this is not the full address, because 64 bits, the full address should be 8 bytes, right? But if you look at it here, it's not 8 bytes. That's why I have 2 zeros at the end. If we do not have that 2 arrows, what will happen? If we do not have the 2 arrows, could be. But if we are lucky, I mean, so without those 2 arrows means we're not going to overwrite those 2 bytes of zeros, right? So whatever is there will be used as address. So whatever is there will be used as address, but we don't know what is there. Maybe it happens to be 0. In that case, we still get a correct result. If it's not, we get segment fault because we're going to jump to an address that exists. So I think most likely it will be a segment fault. Ooh, we do get the flag. That means it happens to be 0 there. Okay, could be some initialized local variable, something. It happens to be 0. Yeah. Oh, actually, another reason is there. Oh, in this case, it's actually guaranteed to be 0 because we are overwriting the return address, and the place we are overwriting, it has a legit return address, right? And the legit return address, the higher 2 bytes is 0. It is 0. Otherwise, it's not legit. Yeah, that's why we're not getting lucky here. Yeah, it's supposed to be this way. Okay, good. Let's move forward. So now you say, by overwriting the return address, we can return into any function in the address space. However, the function we are returning to right now doesn't take any arguments, okay? What if we make this a little bit more challenging? We want to return to a function, and that function takes some parameters. So this is our overflow return to example. It's almost the same as the first one, except that in that print secret function, the print secret function takes one argument, and it compares that argument with this value. Only if that value match, we will print flag. Otherwise, it will print out IP the full. Okay. So let's go to the 32-bit version first. 32-bit version here. The first thing I want to do is disassemble this, try to understand where the buffer is, so we know how much, how many bytes of garbage we should put there. So look at this. We look for the Overflow function. So I can see this. I hope I'm on the right challenge here. Overflow return to, yeah. So this is Overflow. Let's say it's a little bit weird. That doesn't look like the right one. Because here we directly call it. I do not say any compare. Why do I think that here I made a mistake here? Here we have EBP minus E. Move to EAX, then we push EAX. But we never compare that. Oh, sorry. It's not Overflow, it's print secret. Let's go to check a look at print secret. Yeah, Overflow is the same. Print secret here. So yeah. So like I said, 32-bit version. The first argument for the program, for the function is at EBP plus 8. Because EBP points to the old EBP, saved EBP. EBP plus 4 points to the return address. So EBP plus 8 points to the first argument, right? That's why here you can say this is EBP plus 8. We compare EBP plus 8 with that number. Okay, that's how that's what this one is. Okay, so if we look at the Overflow, we can say the buffer is at EBP. Of course, we're talking about different EBP. This one is the Overflow EBP. The previous one was the print secret EBP. So the buffer is at EBP minus E. Okay. So we want to override this one. We need E is what? 14. Okay. We need the 14 bytes of garbage plus 14 bytes of saved EBP. So total 18 bytes of garbage, then 4 bytes of return address, right? So let's say how can we overflow this one? Okay, anyway, before, there are two ways to print out there are several ways to print out the flag here. We can directly return into print flag function, or we can return to print a secret with the correct argument. There is actually a third way to call this, to return, to somehow print out a flag. So anyone, what is the third way here? So the two examples we saw so far, 32-bit, 64-bit, we are returning to the beginning of a function, right? With either the beginning of print secret or the beginning of print underscore flag, right? Yes, so we can directly return to here. That's what I'm saying, yeah. Yeah. Yes, actually, we need to go past the condition, right? We directly go here. So we go past the condition. Since we control the return address, we can return to anywhere. No one said that we have to return to the beginning of the function. So this one, we can either return to the beginning of print secret, but to do that, we need to set up the stack carefully so it has this argument in. We can directly go to the print flag, the beginning of the print flag function, which also give us flag. The second one, the third one is we go to the middle of the print secret function. So we skip this part. Okay, let me show you how to do that. Here we are at print secret. Print secret, there is print flag, right? So we can, previously we were trying to jump here. We don't have to jump here. We directly jump to here. So we bypassed, we skipped the comparison before. Right? This is compare that. We totally skip that. So let's say if that works. So what's the address here? This one is 12F1. This one is 1304. So does it print out the address for us? Oh yeah. So this one is 62F1, which is which is here, F1, right? 62. So we are going to do 6304. Okay, so that the address we need is 6304. So we were to let me write down that address first. 6304. 63. And before that was FF F6. Okay, so how many bytes garbage cleaning? 18 bytes, I remember. 18 bytes of garbage. Plus this. We do this. Okay, this also gives us a flag. However, if we do not go to that address, we go to the beginning of that print secret, which is 12 F1. Okay, this will not give us a flag. Okay, here I'm having 62 F1, which is the beginning of print secret. So when we go there, it will compare that I, and it's not and it's not the predefined value. That's why I say I put it a full. Okay, make sense so far? Okay, now let's move to say how can we set the parameter? However, this approach only works for the 32-bit version, not for the 64-bit version, because 32-bit version, the parameter is on the stack, and you can't override the stack. 64-bit version, the parameter is on the register. There is no way for you to override the register, right? So this is important in the second half of this class, because the return-oriented programming in the ROP, we are going to utilize this feature to do return to mixing. Okay, let's see. How can we do this? This one is a little bit difficult to understand. I try my best to explain here. This one is we are in the Overflow function. The right-hand side is the stack of the Overflow function. In the Overflow function, EBP points to saved EBP. 4 bytes higher than that is return address. Overflow doesn't really have any arguments. So here could be some information from the main function. Anyway, the Overflow doesn't care what this peer is. Then the buffer is somewhere here, lower than the saved EBP. After this, we can, this is what we're going to overwrite. We're going to overwrite the address of print secret here. And the saved EBP, we just put some garbage. The buffer, we just fill it with some garbage. So after that, we're going to return, okay? So what exactly is return? Return, the C code return maps to those 3 instructions. And let's try to understand how this works. The first one is move. Remember, the first one is move EBP to ESP. So after this instruction, both ESP and EBP points to here. Okay. Then it will pop EBP, which means what ESP points to will be popped into EBP. So EBP will have the garbage we put there, which is 4/8. I'm assuming here I put 4/8 there. Then ESP will point to the return address. Now we're going to the return instruction. What the return does, this one does, is to pop what ESP points to, move that to EIP, right? So now EIP has the address of print secret, and the ESP moves 4 bytes up. ESP points to here, okay? Which we don't really care what the value is. However, now what is the next instruction to be executed? It will be the beginning of print secret, right? Now we're here, print secret. So from print secret point of view, it believes ESP points to this same. So the first thing, this will be the beginning of the print secret function, right? It will push EBP, move ESP to EBP, right? So the first instruction push EBP, and remember the value of EBP is what we said, it's AAA there, and it will push EBP. So EBP will be pushed at this address, which will overwrite what we previously have here. So this address will have the AAA. Then it will move ESP, EBP, so both of them points to here. Okay, after this is where this print secret function believe its EBP is, and this is saved EBP. So remember, in any function, if it wants to access its first argument, where should it be? It should be EBP plus 8, right? From the print secret point of view, its first argument would be where at the beginning EBP points to plus 8. So it will actually be here, because this is where EBP is. This is EBP plus 4. This is where it believes it should be its return address, and higher than that should be its parameter or argument. So if we look at this figure, if you really want to overwrite from the buffer, then how much you want to overwrite? You have to fully overwrite the buffer, then 4 bytes here, 4 bytes here, 4 bytes here. You need to overwrite 12 bytes to set this. Okay, but this part you have to at the beginning you have to overwrite it into the return address of the address of the print secret. Okay, so let's try this. This one is a little bit hard to understand. You need to debug this multiple times, try this multiple times, and also after the class, look at my slides back and forth. Okay, we still have several minutes, so let's do this. 2 or 3? 2. Oh, we're already running this, right? So let's see, what do we have here? I should not do that. Nice. So look at this figure. Remember, this is a return address. So how big is the buffer? Buffer is 14, right? So this part is 18, I remember. Yeah. So that part is 18. So we should have 18 bytes of garbage. Then we have the address of the print secret. We have the address of print secret here. Okay. Then these 4 bytes should be the return address for the print secret, but we don't care about that. So we can put another 4 bytes of garbage. Then after that, the parameter should set to that 1, 2, 3, 4 thing. So we add another 4 bytes of garbage here. Then after that, we do that 4 bytes of 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what is the address for? Yeah, let me put something here. We need the address of the print secret here. The address of print secret is let's go. The address of this is F1 62 55 5, 6. Okay, so this should work. So we pipe this into this one. So this is how we get the flag. Because we successfully set the value. If we change this a little bit, it will not work. Okay. We change this a little bit from 78 to 79. It doesn't work. It doesn't generate the flag. Okay. Any questions? Okay, so that is basically what I have for today. So Wednesday, we're going to we're going to extend this. So far we are making calls, returning to function without parameters, and with approach you just saw that, we can basically return to any function with any parameters, any number of parameters, right? But can we return to can we return to a number of functions instead of just return to one function? You already say here, this address is actually will be used by print secret, and we set it garbage. That's why we get a second fault. What if here we set it as something valid? Then we can go into another function, return to another function. But can we do this forever? Can we create a chain of arbitrary number of functions? Okay, let's figure that out this Wednesday. Any questions, folks online? Oh, looks like. Oh, sorry, I was not checking the chat box, so I'm not sure. When you ask, so Xian, you ask why do I get a segment fault? I mean, which specific challenge you are talking about here? You guys can speak, so I can hear you.
In the last challenge, since the print secret is going to exit, right? So we shouldn't get segmentation fault.
The last challenge?
Yeah.
Why do you think we should not get a segment fault?
Because the function is going to exit, so it doesn't have to return anything. So we no need to get any segmentation fault.
Let me see. So after we get flag. Oh, this probably is because the segment fault happens before we call into exit. Because the print secret function calls other functions, and those functions, that time the stack may not may be already compromised. So we haven't reached the exit yet. Well, to answer that, we clearly need to debug to figure out what exactly happens, but I believe that's the case. Yeah.
Okay, Professor, got it.
Give me 1 minute here. Okay. Cool. Any other questions from the online folks? You can, JCM, you can try to debug this. Okay, one way to learn this is to debug. You can debug to figure out why exactly caused the segment fault. Yeah. Okay, see you guys.